To execute multi-step logic, today's LLM-agent serving systems rely on predefined linear workflow templates. These templates dictate the exact sequence of operations an agent must follow to complete a specific task. Because these templates lock operations inside fixed files, their internal structure is hidden from the system. If a user submits a novel query that the system hasn't seen before, it cannot recompose its available operations to solve the problem. It simply returns the closest matching static template. This rigidity forces a severe inefficiency in the memory architecture. Because workflows are isolated from one another, the system must repeatedly cache the KV state of operations that appear in multiple templates. If a basic search step appears in 50 workflows, the system stores 50 separate copies of that KV tensor. This redundant caching consumes massive memory. Storing identical operations repeatedly acts as a ceiling on concurrent requests. Engineers are left with a zero-sum trade-off. Adding more specialized templates to improve task quality directly increases KV redundancy, which degrades serving concurrency. A 2026 paper by Lee et al., titled GraphFlow, addresses this by throwing away the isolated template repository. Instead of storing hundreds of rigid workflows, GraphFlow replaces the entire repository with a single shared global operation graph. This centralizes the data structure, addressing compositional rigidity and memory bloat at the same time. By treating operations, like tool calls or reasoning steps, as atomic, shareable nodes, rather than locked steps in a text file, the serving system gains structural awareness over everything it can execute. We are going to build this pipeline from the bottom up, starting with the shape of this new data structure and ending with the caching math it enables. The principle is one of architectural sequencing. You cannot deploy advanced memory deduplication tricks downstream until you resolve the isolated nature of your data upstream. The substrate of this system is the wGraph. It is a global directed acyclic graph formed by taking every single workflow template in a repository and unioning them together. In this unified graph, every node represents an atomic operation. The edges connecting them represent valid structural or functional dependencies between those operations. Because the system unions the templates, redundant operations collapse. A shared search step that previously existed in 50 separate files now exists as exactly one node in the wGraph. Executable workflows are no longer opaque files. They are simply connected subgraphs routed through this master DAG. This structural shift enables a new approach to caching. Because a shared operation is a single node, the system can pre-compute a single base KV cache for it, using the operation's own standalone description. In legacy systems, that operation's KV state would be calculated and stored redundantly for every active template using it. The memory savings begin with this structural change. By deduplicating operations into a single graph, the system anchors the caching mechanisms we'll examine next. With templates gone, the system faces a routing challenge. When a novel query arrives, the model must find a specific operation path through the wGraph. To solve this, GraphFlow injects a virtual task node, representing the user's specific prompt, directly into the graph, wiring it with bidirectional edges to every single operation node. These bidirectional edges allow the query's context to inform every operation, and allow every operation to relate relic to the query. A graph neural network, or GNN, passes messages across these edges. This folds the task node into every operation, creating embeddings that merge the operation's function with its relevance to the current task. Next, a multi-layer perceptron acts as a scorer. It reads these embeddings and assigns a probability score to each possible edge connecting the operations. Finally, a greedy selection algorithm takes over. It looks at the available connections, picks the highest scoring, structurally valid edge, and expands step by step until a complete workflow subgraph is built. Unlike legacy systems that rely on semantic search to retrieve a static template, GraphFlow generates a custom, topology-aware workflow on the fly. Finding the optimal workflow subgraph is a combinatorial problem. This GNN and MLP mechanism acts as a computationally viable proxy to approximate it in real time. Once the custom workflow is generated, the system has to cache the KV state, as the LLM-agent actually executes the steps. Stateful caching, storing one full cache for every prefix path, causes memory to explode. Stateless caching, storing just one cache per operation regardless of context, breaks the dependencies between steps and lowers accuracy. This equation represents GraphFlow's interpolation between those two extremes. It splits the runtime cache for an operation into a precomputed base, plus a delta matrix capturing the prefix-induced difference. The solid base KV is the exact same tensor we precomputed from the operation's standalone description back in the wGraph phase. The empirical linchpin of this design is the nature of the delta matrix. Research shows that over 75% of the T entries and roughly 70% of the value entries barely change across different execution paths. Because this prefix-induced difference is highly sparse, it is incredibly compressible. The system stores one dense base block and hundreds of tiny, lossy residuals. However, even small residuals carry a scaling risk. If every branching path required a stored residual, the volume would quickly overwhelm the memory capacity. To prevent this, the system uses path pruning. It monitors execution statistics and only materializes these sparse residuals for high-frequency transitions. If a query routes down a rare path, the system stores no residual and recomputes the state on the fly. Combining empirical sparsity with path pruning forces memory consumption to scale only with the active working set, bypassing the combinatorial explosion of complex graphs. To maintain serve-in speed, the architecture is divided. On the left, the heavy offline preparation, building the wGraph, training the GNN scorer, and precomputing all base KV caches. On the right, the online execution per query, augment the task node, generate the subgraph, apply the sparse residual, and serve the agent. Sequestering the graph unioning and precomputations into an offline phase is what allows the per-query workflow generation to execute in real time. The paper tested this architecture on reasoning and coding benchmarks like GSM-8K and math, utilizing 7 to 9 billion parameter models. For quality, GraphFlow achieved a 4.95-point average accuracy increase over AFlow, which was the strongest baseline tested. This chart shows the primary efficiency gain. On GSM-8K, the total KV cache memory footprint drops from roughly 50 gigabytes down to 11. Despite introducing dynamic generation steps, the P90 tail latency is generally lower than the baselines, defying standard memory speed trade-offs. On paper, utilizing a shared substrate accomplishes a rare result: less memory consumption, higher system throughput, and better task accuracy. But systems engineering requires dissecting exactly what that 4x memory reduction actually costs the user. The sparse residual equation is explicitly lossy. When the researchers ablated GraphFlow against full stateful caching on the math benchmark, GraphFlow dropped about 1.2 percentage points in accuracy due to thresholding the delta matrix. There is also an unmeasured risk in path pruning. Forcing cold paths to recompute their state on the fly creates a tail latency risk. Under real-world traffic, this fallback mechanism could spike P90 response times. Furthermore, the evaluation contains an attribution problem. The paper does not cleanly isolate how much of the 4x memory reduction comes from their novel graph deduplication versus standard sequence-level prefix caching already utilized by engines like VLLM. Finally, the system was explicitly motivated by the need to manage long-horizon agents, but it was exclusively tested on short, single-turn benchmarks. Despite these testing constraints, the core contribution holds. GraphFlow proves that generation flexibility and caching efficiency do not require competing architectures. They can read from the exact same unified data substrate. For infrastructure practitioners, the takeaway is clear. The data structure chosen upstream dictates the efficiency of the algorithmic tricks available downstream.